We'll start with the simple harmonic motion. The first point is we need to understand what is displacement and amplitude, period frequency, angular frequency, and phase differences in context of oscillations. So we do have an idea of displacement and amplitude, but in terms of oscillations, in terms of simple harmonic motion, we need to understand where do we find the displacement and where do we find the amplitude. We need to understand this because it's very important in terms of equation application. So, for example, in case of a pendulum, let's say, but this is the ceiling, this is the pendulum at its mean position, and this is its extreme position, and this is the far left position. So mean position will always have a zero displacement, and if you talk about the amplitude, this will be the maximum displacement from the mean position, and it is represented generally in the equations mathematically as x naught. At any other location, for example, at this point, let's say, during this oscillation, right? So at this point, this distance or this displacement will be known as simply the displacement and represented as x. So according to the syllabus, if we look at the displacement, it will be represented as x and amplitude as x naught. And we know period and frequency are linked with the formula that F is equal to 1 over T. That's going to go this way generally. And in the case of pendulum, for example, one oscillation would mean that one time it goes towards the right side from the mean position, then goes back to the left, extreme left, and then comes back to the mean position. This will be one oscillation. It would go the other way around as well. The angular frequency will be taken as omega equals to 2 pi f, and we can also write this down as 2 pi by t. And we are familiar with these formulas from circular motion as well. Then we have phase difference. First, we understand what is phase and how to visualize that. Okay, let's go towards that. Okay, so here we can see an animation from one of the websites. I'll share the link of that website as well. So you can see that what we want to observe is that one wave can be represented as a circle as well. And this equation that we're going to do now will represent that in both terms. So let's play this animation and see how it goes. As we can see that the wave that is being produced on the right side can be visualized as a circle that is represented on the left side. And to understand the phase difference, I'm going to involve another wave in this equation or in this participation animation. Now you can see that there is another wave that is represented as green color. And you can see that over here in the circles, there is an angle between them. There is a difference between them. This is that phase difference that you're trying to calculate in A1 or in AS course, right? And we can see that at any moment, if I pause this animation, you can see that the difference between the waves, either be that from the 0 point or either be that from peak to one peak, this difference is what is represented between these two phasors, right? And if you want to involve another equation, if you want to involve another wave in the system, then that would go something like this. So all of them have a phase difference amongst each other, which is being represented by this angle, which is being represented by this idea. So the thing that we need to understand at this point is that a wave can be represented as a unit circle that is being represented on the left. Okay. So I hope that we understand what is the phase difference. We will calculate that as well later on. And then we have, in the context of oscillations, we need to understand the period, which we just defined over here as omega equals to 2 pi f in terms of both frequency and angular frequency. We know that this is the formula for frequency, and for angular frequency, it will be this one. And then we have what a simple harmonic motion would look like. We will get to that later, but first we need to understand this equation. So phase difference can be taken between the two waves. Either you can compare the two peaks. You have to look at the time frame or the timestamp where they are existing. So let's say this is time t1, this is time t2. And to calculate the phase difference, the formula is very simple. That will be t1 minus t2 or t2 minus t1, the difference of time between them, which is represented as small t sometimes, right? And divided by capital T, which is the frequency for one wave. Now, phase difference can only be calculated between the waves that have same frequency. Otherwise, they will just keep overlapping with one another if the frequency is not same. So if the frequency is same, it does not matter whether you take the time period of this red wave, which will end up eventually somewhere here, or you take the time period of this blue wave. It does not matter because both have the same frequency. So this time period will be from any of the one waves, whichever you are comfortable with, and then multiply this with 360 or multiply this with 2 pi, depending upon if your answer is required in degrees or whether the answer is required in radians, right? That is how you calculate the phase difference between waves. And this is what the animation was actually discussing about, that a wave or the displacement of wave particles can be represented on this unit circle, right? And when we write down the equation, which we will write down just now, that x is equal to x naught, let's say sine omega t, this equation has an omega in it, which is the angular frequency. And this is only visualized over here, that how much angle this wave is actually making if this was visualized as a circle, right? Okay, so we have understood the first point on a general scale. Now we're going to go towards point number 3 first, and then we'll go back to simple harmonic motion, point number 2. Because we need to understand this equation and we need to understand where it comes from and what are the consequent equations as well. So first, we are going to make this graph as a practice to understand what this x equals to x naught sine omega t tells us. Now be advised that this is actually a time equation. So this is a function of time. So x is in reference to t. Now what does this mean? It means that I will put time of my choice, and this whole equation after calculation will tell me what is the actual displacement of that particle at this particular time in frame, right? So let's say, for the sake of example, that the frequency of this system is 50 hertz. So we can find out the time period by dividing this with 1 over 50, and we get 0.02, which becomes 20 milliseconds. I'm going to milliseconds so that the numbers are acceptable in terms of visualization. All right, so over here, let's start with 0 milliseconds. And over here, the timestamp will be 5. Over here, it will be 10. Over here, it will be 15. And over here, it will be 20. Of course, we are actually going to draw the graph somewhere along this line, but so that it doesn't get jumbled up, I've written the times separately. So what does this mean? It means that what you can do now is use your calculator, right, and calculate these values, and it will give you those displacements at those particular instants in time. And but the thing that you need to keep in mind is that your calculator should be in radians mode. It shouldn't be in degrees. I will show this to you by using a calculator, how you can do this, right? Let's see what the settings of the calculators will look like. So you press shift and you go to menu, right? Then you'll get the angle input, press 2, and then he will ask you what is the mode of angles you want. So we want for radians, so we press 2. Now the calculator is in radians. Now I will design the equation exactly this way, like I've taught you before in previous videos, and then we'll go from then we'll continue the video from that point. Okay, so we can see this equation on the calculator right now. What I've done is I've written down this equation as 3 sine. Now we have opened up omega as 2 pi f, and we know the frequency is 50, so we write this down as 2 pi multiplied by 50 and multiplied by x. Now what is this x? This x is timestamp of my choice. Now I know that my full wave is going to get completed in 20 milliseconds, so I can choose any time between 0 to 20. But first we're going to look at 0, 5, 10, 15, and 20 and see what values do we get at these points, right? Since this is a sine function, I know that at somewhere around 5, this will basically be 90 degrees, this will be 180 degrees, this will be 270, and this will be 360, and this is 0 degrees. So I'm expecting a graph like a sine wave, but let's put in the values. So I press calc, and you can notice that I've put in the x over here as the calculator function that I've taught in the previous video. I will attach the link for that video as well. And then I press calc, and then I put in the values of my choice. So at 0, I get 0. So at 0 time, the answer is 0. Then I press calc again. Now notice that this is 5 milliseconds. So I will press in 5e minus 3. So now I get 3. Why did I get 3? Because at this point, the value of this function sine becomes 1. And we will get the maximum amplitude, which is 3. Now you can notice that in place of x naught, I've written down 3, which means that in my situation, in my question, the maximum displacement of my system maximum displacement is 3 centimeters for the sake of example, right? Okay, so that's why you see a 3 over here. It could be a different value for another question as well. And then we are going to get into values. So after pressing calc again, 10 e minus 0, 10 milliseconds, again, I'm going to get 0. So this is going to become 0. Over here at minus 15 or at 15, I expect this value to become negative. And why is that? Because sine at minus 270 becomes negative. So you can see from the calculator it becomes negative 3. So this is negative 3, and consequently at 20 I'm going to get 0. So the graph somewhat goes like this. This will be my positive amplitude, this will be negative amplitude, this is positive and negative. So my graph goes something like this. I'm drawing this in terms of a bit rough draft. Okay. All right. So what has happened at this point? You can see that at timestamps what the values of sine function come out to be. Okay. So this is that understanding of that equation. And after this, one more try. Let's try another value. Let's try a value between 5 and 10, which is 7. So I'm expecting that timestamp to be somewhere along this point, and that value is going to be somewhere less than 3. Let's try that. So calc 7 milliseconds, and you can see that the answer is 2.4, which is going to be at this point, right? So if you go towards 10, your answer starts reducing because it's a sine function. And notice if I take a value between 10 and 15, let's say I take 12. Now at 12, it should be here, and the answer will be negative. Let's try that. So calc 12 minus 3. Now you can see that the answer is negative 1.8, right? So I hope that we understand what this equation actually means, that we're going to encounter that x of t is equal to x naught sine omega t. We will encounter this equation many times in P4 questions, but I hope that we understand what this is and how to visualize it. Then we come towards these derivations and understanding. Now this is, the first graph is related to displacement, simply. The second one is related to velocity, and the third one is related to acceleration of those simple harmonic motions. Now, we are most definitely discussing it in terms of a pendulum, in terms of an oscillating trolley, in terms of a spring, in terms of, let's say, electrons movement in an AC supply. They are also simple harmonic motion. But first, let's do the mathematical derivation that is the needful, and then we're going to go towards simple harmonic motion. So the equation for displacement was given to us as x of t is equal to x naught sine of omega t. Now, we know that velocity is actually the rate of change of displacement with respect to time. So if I take the derivative of this function, which is this one, which is already given to me, then that becomes, you need some mathematical knowledge to do this. This becomes x naught. Then we have the derivative of the sine function, which is cos of omega t. The whole function comes as it is. And then we have to take the derivative of the angle as well, because the derivative with respect to what we are taking is time. And that time, or that t value, exists in the angle. So then we take the derivative of this, that becomes simply omega. So this equation comes down as x naught omega cos of omega t. And then we know that if we take the derivative of velocity, now this becomes the velocity of t, or velocity at time t. If we take the derivative of velocity with respect to time again, it gives us acceleration. So we have to take the double derivative at this point of this equation again. So these are the constants. They will take part as it is. So this becomes x naught omega dot. Now the derivative of cos function is negative sine. So this will be negative sine. Again, omega t will be part as it is. And then the derivative of the angle itself, that will be omega only. So this becomes a negative will be taken on the outside. This becomes negative x naught omega square sine of omega t. Now notice that these graphs that we have just selected at this point, you can see that this is a sine function graph. This is a sine graph. That's why the function is sine. And this is a cosine function graph. That's why we get the derivative as cos. And this actually looks like a sine graph, the acceleration, but inverted, the negative sign, right? That's why we see a negative sign at this location. Okay. Now, this is one way to look at these derivations. There is another perspective to look at them, and that is the gradient function. Now, we know that we have been finding these next derivations with reference to the gradient, with reference to the derivative, and we know from mathematics that derivatives actually give us the gradient function, right? So if I visualize the displacement for the first time frame that the gradient is maximum, or it has a slope, we can see that gradient being maximum means that the velocity is going to be maximum. Similarly, when the gradient becomes zero at this point, when displacement is at 90 degrees, the velocity, so the gradient is zero, so the velocity also becomes zero at this point, right? So even at this point, even in this graphs, we can visualize the gradient or the slope to actually give you the information of the velocities or respectively accelerations as well. And one thing that you need to notice is that the displacement and the acceleration graphs will actually be opposite to each other no matter what situation you're in, either pendulum, spring case, or any other case, right? Okay, so we have done these derivations. Now let's go back to the simple harmonic motion. That was point number 2. So we've understood what is x omega naught sine, right? We've understood the velocity equations as well. We are skipping these displacement equations for now deliberately. We'll get to that later. Let's do that point number two, that is simple harmonic motion. So now be advised that all of the oscillation means that an object repeats or continues its motion between two positions, right? But which one of them are going to be called simple harmonic motion? They need to satisfy two conditions. Anything can be an oscillation, any repeated movement can be an oscillation, but for it to be called a simple harmonic motion, it needs to fulfill these two conditions. And what are those two conditions? The conditions for simple harmonic motion, the first one is that the acceleration should be proportional to displacement. What does that mean? We'll get to that later. And the second condition is that acceleration should be proportional to the negative of displacement. Negative of displacement. What does that mean? It means that wherever the acceleration is taking place, it should be in the opposite direction to the displacement. And we'll get to that understanding as well. So let's consider this case of a spring in this one to make it easy to understand. Now, if I compress, let's say, if I stretch the spring at a larger location, for example, most definitely the spring is going to try to come back to its original position. So what's happening at this point? What you have tried to do is you have tried to produce a negative displacement, negative x, but your acceleration is in the positive direction. And of course, we're talking in terms of vectors. We know that right and upwards are positive, down and leftwards are negative, right? So we're talking about in that reference. And if, let's say, you try to compress the spring by pushing it upwards, so now the displacement is positive because it has moved upwards, but the spring is going to try to stretch open. It's going to try to oppose you to come back to its original position, which is unstretched length. So in this situation, the acceleration or the force eventually will be in the negative direction. Where is the acceleration coming from? We know that it is coming from F equals to ma. And where is the force coming from? In the case of the spring, it's coming from kx due to Hooke's law, right? So we know where the force is coming from and where the acceleration is going to exist, and in what reference we are talking about acceleration. And the other thing is about the relative displacement. So the first point says that if you are very far away, if your displacement is very high from the main position, then your acceleration will also be high. And it is very evident in this situation. If you try to stretch the spring more and more, if this was the main position, let's say, unstretched position, if you try to stretch the spring more and more, if you try to move away from the spring more and more, then you're increasing the displacement. And we know that if you increase the displacement of the spring, the restoring force or the force of the spring, the stretching force also increases. And if the force is increasing, then most definitely the acceleration will increase. So in the case of a spring and in the case of the pendulum, we'll analyze the pendulum later. These two conditions are being fulfilled. The displacement and the acceleration should be in the opposite direction. That if you want to go right, the acceleration should be left. And if you're on the left, the acceleration should be on the right. Similarly, and as far as you go from the main position, if you're very, very far away, then the acceleration or the factor that is trying to take you back to the main position should also get stronger, right? So these are the two conditions for SHM or simple harmonic motion. We've done the derivations as well. And now we're going to look at these graphs in terms of an oscillating spring. That if a spring is oscillating upwards and downwards, how do these graphs actually look like? Now, notice that on the right side, we have the respective quantity, which is whatever on the y-axis, and we have time, right? So these equations are actually going to be time functions. So x naught sine omega t. Over here, this will be x naught omega cos of omega t, the derivation that we've just done. And this one is going to be x naught omega squared with a negative sign, again with sine omega t. These are time functions because we have time on the x-axis. But if we come to the left side, we see that these are displacement functions, right? So the displacement function equations for these factors simply are taken from these equations. That was v is equal to this equation, and then a is equal to this one. So what we've done in this situation is we're eliminating time, and we are going to involve displacements. So the equation for displacement reference of velocity comes out as omega under root x naught squared minus x squared. And over here, the acceleration equation in terms of displacement comes out as negative omega squared x naught. Now, x naught could be any x. You can take any displacement, right? And again, in terms of the pendulum or in terms of the spring, if you try to discuss this, let's talk about the spring. Let's say that this is the unstretched length of the spring, right? Before oscillation. If you try to, let's say, stretch it, let's say this is the new position, and if it's stretching upwards, that is this position. So this is my mean position of the spring, right? And if you're talking about x naught in any system or any situation, that will be the maximum displacement. It could be either in this situation or it could be either on this side. It could be in any side. So this will be the x naught. And any other displacement during its motion, for example, let's say it's existing at this point. So this will be taken from the mean position as x. So you put in x of any other displacement, you put in the maximum displacement, and then you can find the velocity at that exact location. The same thing happens with the pendulum as well, that for a pendulum, let's say this is going to be the maximum displacement as x naught, and the pendulum existing at any other location will be taken as simple x. And you can place those equations or values of displacement in these equations, and you will get that answer for that respective situation of acceleration. So be advised, the left-hand side of the graphs are actually displacement and a respective quantity. The right-hand side are actually time-dependent. I'm going to show you an animation in terms of the springs oscillation, right, and the respective graphs, how they look like. Okay, so you can see on the left one of the animations of the spring that is hanging, right? Now, please notice that this is our mean position, right? This is our standard position, and this is one of the extremes of the displacements, right? And the other one is the other displacement, right? So this will be the maximum displacement x naught in the mathematical equation that we are using, and this will again be one of the displacements. Now notice the arrows that are being represented over here in terms of yellow and black, right? So let's pause this animation for a second, right? Now at this point you can notice that the yellow arrow is downwards and the black one is also downward because they are representing force and acceleration. Notice that we are actually in the positive displacement side, right? We are on the positive displacement side. This region is in the positive displacement and this one is in the negative displacement. But notice if we are in the positive displacement region, the force is acting downwards in the negative direction, and so is the acceleration. Similarly, when this actually comes down, let's let it play. At this location, for example, we can see that the displacement is negative because it's actually moved downwards from the mean position. But the direction of the arrows of the forces is in the upwards direction, which is going to be the positive direction. This is simple harmonics motion's condition, that acceleration and displacement should be in the opposite direction, which we see as A being proportional to negative displacement. And the second condition was acceleration being proportional to displacement, that if it is very, very far away from the mean position, then the value of acceleration should increase. And let's see how that is happening, right? So if we remove all of these and we consider new mean positions, for example, this is the lower extreme, this was the upper extreme, right? Okay, so As it starts to move, let me clear this out. As it starts to move upwards, the second law is what we're trying to explore. So if you try to move away from the mean position, the acceleration will increase, which means that the restoring force should also increase, right? A more, it's going to make more and more effort if you try to move away from that position. Okay, so let's play this one by one. Now, as you can see that as it moves closer to the mean position, the value of restoring force starts to decrease. So if you are closer to the displacement, to the mean position, if you are close to the mean position, the value of x is small, so the value of acceleration will also be small. But if you're very far away from the mean position, the value of x is higher, acceleration will also be higher. So if any system follows these two principles or these two ideas, that means that that motion is actually simple harmonic motion. That's all that we are interested in, right? Okay. Now let's try to visualize these graphs that are on the right side of velocity and of this spring motion as well. First, we will link the spring motion with what this animation has represented to us, right? Let's try to do that. So I'm going to play both animations and you have to visualize them. So only for the now, focus on this side, this one, and match this with the spring, how this one goes about, okay? So this upward side of velocity and displacement is actually representing the motion of the spring, right? So I'm going to minimize the motion of the spring and we're just going to visualize these displacement graphs and these graphs only, right? Now you can see the animation as well, how it is moving with reference to time. These are all animations in terms of time, like I've shown in this slide as well. And the left side is in terms of displacement, right? So notice that this will be my maximum negative displacement, and this will be my maximum positive displacement of the velocity. And this equation, or this is actually being dealt by the equation of V is equal to omega under root x naught squared minus x squared. I can choose any x of my choice. It could be anything, right? And it will either give me this answer or it can give me this answer. Why? Because we know that the under root function in mathematics gives us an answer in positive and negative both ways. It's going to be your job to understand or identify whether the spring is moving upwards or downwards. For example, whether the spring or whether the pendulum is coming towards this side or is it coming from this side. Depends on the motion, right? So no need to worry about these two answers coming in terms of velocity. It doesn't matter, okay? So similarly, on the other side, you can put in, let's say, the displacement from this side. And of course, if you put in the negative displacement, it does not matter because of the square, it will be eliminated, right? Okay, on this side, we have the acceleration and displacement equation, which is going to be A is equal to minus omega squared x naught. Now, be advised that most definitely, we are talking about this displacement being any displacement. So in these extreme positions, we know that the displacement is actually negative x naught and this is positive x naught. I can choose any other displacement, put in that in this equation, and it will tell me what will be the acceleration at that exact instant, right? In these systems, omega is taken to be constant. It's not changing. And on the other hand, we have these velocity and time equations and acceleration time equations, and we've done those as well. So, for example, if we have V is equal to x naught omega cos of omega t. Now, I will put time of my choice and it will tell me the exact velocity at that timestamp. It is going to be my choice. I will choose that time, what I'm going to put in the equation, and it will tell me the velocity at that time. So the question can either be given to you in terms of a time equation or it can be given to you in terms of a displacement equation. But be advised, generally we find the displacement equations to be more easily solvable and more frequently the question is going to be asked in this term, right? Okay. So now I hope what these graphs actually meant from the animation, right? Okay. Now moving towards these common oscillating systems. So we have observed the spring system, how it moves, and exactly the same way it's going to go in the trolley system as well. So this will be the mean position, and how far back it can go because of the two springs will be taken as x naught, and any other displacement will be taken as x in these velocity and acceleration equations. Okay. All right. Now we move towards the pendulum system. This is what we were talking about at the very beginning. We have to identify, let's say, whether this is an SHM or not, whether this is simple harmonic motion or not. Now, if we analyze this in terms of that mean position, right, and we analyze the components, we realize that it has two components. It has only one component, for example, and that is of the weight. And if we look at this angle, for example, let's say this angle is theta. I'm ignoring the black line for now. Then we have two components. One of them is going to look like this, and one of them is going to look like this. And we've done this in vector components as well. So whatever theta is this, that will be this theta as well. And the angle or the component in front of the angle is basically mg sine theta. Let's make the component for the second pendulum as well. So again, the weight is downward, which is mg, and this is its theta in blue color. Then this will be one of the components, and this will be the other component. Now we can notice that this green theta 1 and theta 2, we know that theta 1 is greater than theta 2. Sorry, it's the other way around. Theta 2 is greater than theta 1. This will, let's say, be a 60 degrees angle, and this will be maybe a 30 degrees angle, right? We know this by looking at this. So let's say this is theta 2, right? So the component in front of the angle becomes mg sine of theta 2. Now, let's compare mg sine theta 1 and sine theta 2. We know that if we are comparing them, for example, then mg sine theta 2, we know that mg is going to get cancelled out from both sides because it's same for both of them. Then it's all down to sine of theta 1 being compared to sine of theta 2. And since we know that theta 2 is greater than theta 1, that means that this side will be greater than that side. Now, how does that justify that this is simple harmonic motion? You see, simple harmonic motion, first condition was that acceleration should be negative of displacement. They should be in the opposite direction. And that is the case in this situation as well. You see, the displacement is on the right side, so the displacement is positive. But the factor that is responsible for taking it back to the mean position is mg sine theta. So the force is being exerted in the negative direction while the displacement is in the positive direction. And of course, why we are talking about force? Because we know that this is proportional to acceleration. Right? So if we talk about force, we're talking about acceleration as well. So the first condition is fulfilled, that they're in the opposite direction. The second condition is that acceleration being proportional to displacement. If you move away from the mean position, the acceleration should be higher. And we can see that over here, if we start moving away from the mean position, the more we move away, the more theta increases. The more theta increases, the more the value of mg sine theta increases. And we know that this is the value of force. Mg sine theta is force because it's a component of weight. And if the force is increasing, that means that the acceleration is increasing. So the second condition is also fulfilled. If you start moving away from the mean position or from the mean position, your displacement starts increasing. If your displacement is increasing, the restoring force, why we talk about restoring force? Because that is a force responsible for bringing it back to the mean position, also increases, right? So both conditions are being satisfied in this condition. So this is a simple harmonic motion. This is exactly the same displacement and acceleration graph that we just did in this slide. If you can notice, this is that graph. So I will recommend you go back to the animation, go back to the video and animation, and observe how this graph is actually being formulated. A few key points. Since the acceleration is equal to negative omega square x naught, we know that there is a negative, so the gradient of this equation will be negative. And I know that on y-axis is acceleration, so y is equal to mx, and x naught is in the displacement, and omega square is the gradient. So the gradient is constant in throughout the system, which is one of the common misconceptions students have. Gradient is constant or omega is constant in all of these systems. Again, if you notice that the displacement is negative, but the acceleration is positive. Again, simplifying, or you can say satisfying the simple harmonic condition. If the displacement is positive, then the acceleration comes out as negative. Again, in tune with this equation and idea that we've already have. Okay. Moving on towards the energy of simple harmonic motion. This is one of the topics that we need to understand a bit more deeply. So I will be making a separate video of this, right? So that is a simple harmonic motion, and its graph and its understanding is going to be up to this point. A second part will cover the energy graphs, which will continue from exactly this point onwards, right? I hope you have understood what is simple harmonic motion, how to visualize the graphs and situations.